Hello everyone. Today we'll study multi-variable probability density function. First of all, before the class, let's do some review for calculus. First example. Find the area between the curves. Y equal to 2s plus 1 and y equal to s squared minus 2. Find the area between the curves y equal to 2s plus 1 and y equal to s squared minus 2. In order to find the area between curves, let's first of all draw the graph first. Draw the curves first. Let's draw the curves first. First curve, y equal to 2s plus 1. That's a straight line. Y-intercept is 1, slope is 2. That's a straight line. Y-intercept is 1, slope is 2. That's a straight line. Y equal to 2s plus 1. Another curve, y equal to s squared minus 2. Y-intercept is negative 2, and it's a parabola open upward. Y-intercept is negative 2. It's a parabola open upward. That's the second curve, y equal to s squared minus 2, which is a parabola open upward. Y-intercept is negative 2. We're looking for area between these two curves. In order to find area between curves, we use upper curve minus lower curve. In order to find area between the curves, we use upper curve minus lower curve. Here, upper curve is the straight line, 2s minus 1. 2s plus 1, that's an upper curve. Lower curve is a parabola, s squared minus 2. Use upper curve minus lower curve. Then take integral from left endpoint to the right endpoint. Take integral from left endpoint to the right endpoint of the region. This is region R. We're looking for area of this region. We use upper curve minus lower curve. Here you can see the upper curve is the straight line. Lower curve is a parabola. Use upper curve minus lower curve. Take integral from left endpoint to the right endpoint. How do we find the left endpoint and right endpoint? Here we can see that left endpoint and right endpoint, they are the intersection of these two curves. The left endpoint and the right endpoint, they are the intersection of these two curves. So I can set these two equations equal to each other. I can set 2s plus 1 equal to s squared minus 2. Set this equation equal to each other. Solve the equation for x. We can find the left endpoint and right endpoint. So this equation can be rewritten as s squared minus 2x minus 3 equal to 0. If I factor, I get s minus 3 times s plus 1 equal to 0. Solve the equation s equal to 3, s equal to 1, s equal to negative 1. So left endpoint, here x is negative 1. Right endpoint, here x is 3. So take integral from negative 1 to 3. Then solve the integral. If I combine like terms first, I have 2x plus 3 minus s squared dx. Then take antiderivative. I get s squared plus 3x minus s cubed over 3. Evaluate from negative 1 to 3. If I plug in 3, I get 9 plus 9 minus 9. If I plug in negative 1, I get 1 minus 3 plus 1 over 3. Then I use my calculator. I get 32 over 3. That's the area between these two curves. Next example, find the area between curves y equal to x squared, y equal to x minus 1, y equal to 0, and y equal to 1 in quadrant 1. In order to find area between curves, let's draw the curves first. Let's draw the curves in quadrant 1. Y equal to x squared in quadrant 1 is a parabola. Y equal to x minus 1. That's a straight line. Y-intercept is negative 1. Slope is 1. That's a straight line. Y-intercept is negative 1. Slope is 1. That's y equal to x minus 1. Next, y equal to 0. That's a horizontal line passing through 0 in the y-axis. That's a horizontal line passing through 0 in the y-axis. Y equal to 1. The graph is a horizontal line passing through 1 in the y-axis. The region bounded by the curves is this region here. That's the region bounded by these four curves. Let's call this region R. How do we find the area of region R? To find the area of region R, there are two ways to find area. We can use upper curve minus lower curve, or we can use right side curve minus left side curve. Here, can we tell what's the upper curve, what's the lower curve in region R? In region R, in this region here, the parabola is upper curve. The line y equals 0 is a lower curve. In this region here, the line y equal to 1 is the upper curve. And the line y equal to s minus 1 is a lower curve. Since in different regions we have different upper and lower curve, it's hard to find the area using upper curve minus lower curve. Now let's think of the area, finding area using right side curve minus left side curve. Let's think of finding area using right side curve minus left side curve. In region R, in the entire region R, we can clearly tell this is the left side curve. The parabola is the left side curve. In a straight line, it's a right side curve. Over the entire region, that's the left side curve. That's the left side curve. Left side, right side. And the boundary is from 0 to 1. So in this example, using right side curve minus left side curve will be much easier. And the bound is from y equal to 0 to y equal to 1. So if I'm using right side curve minus left side curve, I take integral from 0 to 1. If we're using right side curve minus left side curve, we must write x in terms of y. If we use upper curve minus lower curve, we write y in terms of x. If we use right side curve minus left side curve, we write x in terms of y. So in the parabola, if I get x by itself, I have x equal to radical y. That's the left side curve. For the straight line here, if I get x by itself, I have x equal to y plus 1. So I use right side curve minus left side curve. I get y plus 1 minus square root of y. Right side curve minus left side curve. dy. Y varies from 0 to 1. Y varies from 0 to 1. Then take antiderivative. We get y squared over 2 plus y minus y raised to 3 over 2 divided by 3 over 2, which means multiplied by 2 over 3, the reciprocal. Evaluate from 0 to 1. If I plug in 1, I get half plus 1 minus 2/3 If I plug in 0, I get 0. Then I use my calculator. The answer is 5 over 6. That's an area between these four curves. Next, I want to show you how to use double integral to find area between curves. Redo the above problem. Using double integral. For the above problem here, we try to find area between the curves y equal to 2s minus 1 and y equal to s squared minus 2. In order to find area between curves using double integral, we have two choices. We can integrate from bottom to top or from left to right. For any region, if we can clearly tell the upper and lower curve, then we can integrate from bottom to top. But if we can clearly tell the left side and right side curve, then we integrate from left to right. In this region R here, it's unclear what's the left side and what's the right side curve. In this region, it's unclear what's the left side, what's the right side curve. But it's very clear, the straight line is the upper curve, the parabola is the lower curve. So we can integrate from bottom to top. When we integrate from bottom to top for each curve, we write y in terms of x, which we have already. Write y in terms of x. Integrate from bottom to top. Lower curve is y equal to s squared minus 2. Upper curve is y equal to 2s plus 1. Lower curve is the parabola y equal to s squared minus 2. Upper curve is y equal to 2s plus 1. Then the x-bound is from -1 to 3. From left endpoint to right endpoint, x-bound is from -1 to 3. S-bound is from -1 to 3. Then the inner integral is dy. We must match the variable. Inner integral is dy. For outer integral, we take dx. For double integral, we start from inner. Now if we try to solve for inner integral, we are taking antiderivative with respect to y. We are taking antiderivative with respect to y. So leave an outer integral the same. Leave an outer integral the same. Take inner integral with respect to y. If I take antiderivative with respect to y, antiderivative of dy is y. Evaluate y from x squared minus 2 to 2s plus 1 dx. Then plug in the upper and lower limit and take difference. Plug in the upper and lower limit and take difference. S is from -1 to 3. If I plug in the upper limit for y, I get 2s plus 1. If I plug in lower limit for y, I get x squared minus 2. Then simplify. X is from -1 to 3. If I combine like terms, I have 2x plus 3 minus s squared dx. Then take antiderivative with respect to x. I get s squared plus 3x minus s cubed over 3. Evaluate from -1 to 3. If I plug in 3, I get 9 plus 9 minus 1. If I plug in -1, I get 1 minus 3 plus 1/3. Then use calculator, I get 32 over 3. Which is the same answer as we have here. So using double integral, we get exactly the same answer as using single integral. Using double integral, we get exactly the same answer as we're using single integral. Next example. Let's redo example 2 using double integral. In example 2, we try to find the area between the curves y equal to s squared, y equal to s minus 1, y equal to 0, and y equal to 1. In order to use double integral to find areas, we have two choices. We can integrate from bottom to top or left to right. If we can clearly tell the lower curve and upper curve, we can integrate from bottom to top. If we can clearly tell the left side curve and right side curve, we can integrate from left to right. Here in region R, in this region here, that's an upper curve, that's lower curve. In this region here, that's upper curve, that's lower curve. Since in different regions we have different upper and lower curve, it's hard to integrate from bottom to top. Now let's think of integral from left to right. In this region R, we can clearly tell the parabola is a left side curve. The straight line is a right side curve. So if we can clearly tell left side and right side curve, we try to integrate from left to right. We try to integrate from left to right. If we integrate from left to right, left side curve is x equal to radical y. That's left side curve. Right side curve is x equal to y plus 1. If we try to integrate from left to right, we must write x in terms of y. If we try to integrate from left to right, we must write x in terms of y. If we integrate from bottom to top, we must write y in terms of x. If we try to integrate from left to right, we must write x in terms of y. Then the y bound here is from 0 to 1. The y bound is from 0 to 1. Now match the integral here. The inner integral must be dx. Outer integral must be dy. Now, we solve the inner integral first. When we solve the inner integral, we take antiderivative with respect to x. When we solve the inner integral, we take antiderivative with respect to x. If I take antiderivative for dx, I get x. If I take antiderivative for dx, I get x. X varies from radical y to y plus 1. Leave an outer integral the same. Then we plug in upper limit and lower limit for x, and then subtract. If I plug in upper limit, I get y plus 1. If I plug in lower limit, I get radical y dy. Then take antiderivative with respect to y. Then take antiderivative with respect to y. I get y squared over 2 plus y minus y raised to 3 over 2 times the reciprocal. That's 2/3. Evaluate y from 0 to 1. Evaluate y from 0 to 1. If I plug in 1, I get half plus 1 minus 2/3. If I plug in 0, I get 0. Then I use my calculator. I get 5 over 6, which is exactly the same as we're using single integral. So using double integral and single integral, we can get exactly the same answer. Next, let's practice more about double integrals. Because for many problems related to multivariable probability density function, we have to use double integrals. Let's practice more about double integrals. Next example. Evaluate the double integral over region R, f of sy dA, where f of sy equal to x plus y, and R is the region 0, 2, interval 0, 2, cross the interval 0, 4. How to evaluate this double integral? First step, draw region R. Region R is the Cartesian product, interval 0, 2 cross interval 0, 4. 0, 2, that's the interval in the x-axis. 0, 2, that's the interval in the x-axis. 0, 4, that's the interval in the y-axis. If we find a Cartesian product, There's a region. There's a region R. Cartesian product 0, 2, Cartesian product 0, 4. That's region R here. Now, how do we take integral over region R? How do we take integral over region R? We have two choices. For double integral, we have two choices. We can integrate from bottom to top or left to right. Here, we can clearly tell that's a lower curve. Lower curve is the y-axis. Lower curve is s-axis, y equal to 0. Upper curve is this line, y equal to 4. We can clearly tell that's a left side curve. That's a lower curve. That's an upper curve. And also, we can also tell this is left side curve. That's right side curve. So in this region R, it doesn't matter. We can integrate from bottom to top or left to right, doesn't matter. Answer should be the same. So if we integrate from left to right, if we integrate from bottom to top, lower curve is y equal to 0. Upper curve is y equal to 4. Then S bound is from 0 to 2. F of sy is s plus y. Then we must write dy first. We must match the integral here. dy, then dx. Here we integrate from bottom to top. Or we can integrate from left to right. If we integrate from left to right, we can tell that left side curve is the y-axis, which is s equals 0. Right side curve is the vertical line that passing through 2, which is s equal to 2. If we integrate from left to right, we have s equal to 0. Left side curve is s equal to 0. Right side curve is s equal to 2. Then the y bound is from 0 to 4. F of sy is s plus y. Then we try to match the integral. We must do dx first, then dy. If we solve these two integrals correctly, answer must be exactly the same. If we solve both integrals, answer must be exactly the same. So let me show you how to solve both integrals. Let me solve the first integral first. Let me put the second integral here. I'll solve it later. If we solve the first integral, we do the inner integral first. Take antiderivative with respect to y. Take antiderivative with respect to y. That means I treat x as constant. Leave outer integral the same. Take antiderivative with respect to y. I treat x as constant. If I take integral with respect to y, I have sy here, because I treat s as constant. If I take antiderivative for y with respect to y, I get y squared over 2. Evaluate y from 0 to 4. Then plug in upper and lower limits for y. If I plug in 4 for y, I have 4x. 4 squared is 16. 16 over 2 is 8. If I plug in 0 for y, I get 0. Then take antiderivative with respect to x. I get 2x squared. Minus ax. Evaluate from 0 to 2. If I plug in 2, 2 squared is 4, 4 times 2 is 8. If I plug in 2 here, 8 times 2 is 16. If I plug in 0, I get 0. 8 plus 16 is 24. So if I take integral from bottom to top, answer is 24. That's the value of this double integral. Now, another way. If I take integral from left to right, answer should be exactly the same. If I take integral from left to right, it should be exactly the same. That's left side curve, that's right side curve. And the y bound is from 0 to 4. Now, if I take integral from left to right, I do dx first. Solve the inner integral first. Take antiderivative with respect to x. leave the outer integral the same. If I take antiderivative with respect to x, I get x squared over 2. Here I treat y as a constant. If I take antiderivative for y, I get y times x. Evaluate x from 0 to 2. If I plug in 2 for x, 2 squared is 4. 4 over 2 is 2. If I plug in 2 for x, I get 2y. If I plug in 0 for x, I get 0. Then take antiderivative with respect to x, I get 2y plus y squared. Evaluate y from 0 to 4. If I plug in 4, I get a plus 16. If I plug in 0, I get 0, which is 24. So it doesn't matter if we integrate from left to right or bottom to top, answer should be the same. Next example, evaluate the double integral of f of sy over region R, where f of sy is 3x minus 12y squared, and the region R is the set of sy in R2, where x is between 0 and 1, and y is between 0 and x. In order to evaluate the double integral, let's first of all draw region R. Let's draw region R first. Here R is the set of all sy in R2, where x is between 0 and 1, and y is between 0 and x. How do we draw region R? We know that here x is between 0 and 1. That's easier. How do we graph that y is between 0 and x? Y is between 0 and x, that means y is between y equal to 0 and y equal to x. Y equal to 0 is an x-axis. This is y equal to 0, that's an x-axis. Y equal to x is a straight line. And it's bounded by s equal to 1. It's bounded by s equal to 1. It's bounded by this line, s equal to 1. So this line is y equal to x. Y is between 0 and x. We have all region between these two curves. Y is between 0 and x. This is region R. In order to take double integral over region R, we have two choices. We can take integral from bottom to top or from left to right. If we integrate from bottom to top, we can clearly see that y equal to 0. Y equal to 0 is a lower curve, and y equal to x is an upper curve. If we integrate from bottom to top, that's a lower curve, and that's an upper curve. X varies from 0 to 1. X is from 0 to 1. In this region R, x is from 0 to 1. F of sy is 3x minus 12y squared. Then match the integral. We must take dy first, then dx. That's how we integrate from bottom to top. For region R, we can also integrate from left to right. If we integrate from left to right, we can clearly see that this is the left side curve, and this is the right side curve. If we integrate from left to right, we can clearly see that this is the left side curve, this is the right side curve. For the left side and right side curve, we must write x in terms of y. So for the left side curve, if I write x in terms of y, I have s equal to y. For the right side curve, this is the line, s equal to 1. So if we integrate from left to right, left side curve is s equal to y. Right side curve is s equal to 1. That's left side curve. That's the right side curve. And y, from outer bound, y varies from 0 to this point. At this point here, since x is 1, y equal to x, y must also be 1. So from outer bound, y is from 0 to 1. F of sy is 3x minus 12y squared. Then match the integral. we must have dx first, then dy. So that's how we integrate. That's how we integrate from left to right. That's how we integrate from bottom to top. That's from left to right. If we solve both integrals, the answer must be the same. If we solve both integrals, the answer must be the same. Here, let's solve both of them. If I solve this integral here, I must solve the inner integral first, which means take antiderivative with respect to y. Take antiderivative with respect to y. That means I treat s as constant. So leave an outer integral the same. Take antiderivative with respect to y. So 3x, we treat 3x as constant. Antiderivative of 3x is 3xy minus 12y squared. If I take antiderivative with respect to y, I have 4y cubed. Evaluate y from 0 to x times dx. Then I plug in the upper and lower limit. If I plug in upper limit, I plug in x for each y. I have 3x squared. If I plug in x for y, if I plug in x for y, I have minus 4y cubed. And it's 4s cubed. If I plug in x for y, I have 4s cubed. If I plug in 0, I get 0 dx. Then take antiderivative with respect to x. I get s cubed minus x to the power 4. Evaluate from 0 to 1. If I plug in 1, I get 1 minus 1. If I plug in 0, I get 0. So the answer is 0. Now, if I solve this integral, I should get the same answer. I should get exactly the same answer. Let's solve it. For this integral, I take the inner integral first. Take antiderivative with respect to x. So I leave outer integral the same. Y is from 0 to 1. Take antiderivative with respect to x. I get 3x squared over 2. Since I treat y as a constant, I get 12y squared times x. Evaluate from s equal to y to s equal to 1. Then I plug in 1 and y and take difference. If I plug in 1 for x, I get 3 over 2. If I plug in 1 for x, I get minus 12y squared. If I plug in y for each x, I get 3y squared over 2 minus 12y cubed dy. Then I combine like terms. This term and this term here, they are like term. Negative 12 plus negative 3 over 2. That's negative 27 over 2 times y squared plus 3 over 2 plus 12y cubed dy. Then I take antiderivative. I get negative 27 over 2 times y cubed over 3 plus 3 over 2 times y plus 3y to the power 4. Evaluate from 0 to 1. Then I plug in 1 and 0 and take difference. If I plug in 1, I get negative 9 over 2 plus 3 over 2 plus 3. If I plug in 0, I get 0. Then negative 9 over 2 plus 3 over 2 is negative 6 over 2, which is negative 3. Negative 3 plus 3 is 0. 0 minus 0 is 0. Answer is 0. So for double integrals, it doesn't matter if we integrate from left to right or bottom to top. The answer must be the same. Next example. Evaluate a double integral f of sy over region R, where f of sy is s squared times y, and region R is the set of sy in R2, where x is between 0 and 2y minus y squared, and y is between 0 and 2. In order to evaluate a double integral over region R, let's first of all draw region R. How do we draw region R? Here R is the region of sy in R2, where x is between 0 and 2y minus y squared, and y is between 0 and 2. Y is easy, between 0 and 2, that's easy. Y is between 0 and 2, that's easy. How do we graph that x is between 0 and 2y minus y squared? X is between 0 and 2y minus y squared means x is between s equal to 0 and s equal to 2y minus y squared. S equal to 0 is the y-axis. That's y-axis. S equal to 2y minus y squared. That's a parabola. That's a parabola. That's a parabola. S equal to 2y minus y squared. And s is between these two curves. S is between 0 and 2y minus y squared. That's region R. That's region R. Now, how do we take double integral here? For the double integral, we can clearly see that the left side curve is s equal to 0. Right side curve is s equal to 2y minus y squared. If we integrate from left to right, left side curve is s equal to 0. Right side curve is s equal to 2y minus y squared. And the y bound, y is from 0 to 2. For region R, y is from 0 to 2. F of sy is s squared times y dx dy. For this region R, can we integrate from bottom to top? For this region R, can we integrate from bottom to top? From bottom to top, in region R, can we tell what's a lower curve, what's an upper curve? Lower curve and upper curve is the same curve. It's the same function. What can we do here? If we really want to integrate from bottom to top, for the lower curve and upper curve, we must get y by itself. In this equation, we must get y by itself. S equal to 2y minus y squared. In this equation, how do we get y by itself? How can we get y by itself? So let me first of all move y to the left side. Move x to the right side. Then I can try to complete squares. In order to solve for y, I can try to complete squares. I can add 1 to both sides. Then I have y minus 1 squared equal to 1 minus x. If I take square root, y minus 1 equal to plus or minus radical 1 minus x. If I solve an equation for y, by moving 1 over, I have y equal to 1 plus minus radical 1 minus x. So the upper curve is y equal to 1 plus radical 1 minus x. Lower curve is y equal to 1 minus radical 1 minus x. That's an upper curve, that's a lower curve. So if we try to integrate from bottom to top, lower curve is y equal to 1 minus radical 1 minus x. Upper curve is 1 plus radical 1 minus x. What's the bound for x? X is from 0 to this point. What's x here? What's x here? At this point is the intersection of these two curves. This point here is the intersection of these two curves. So I can set the upper curve equal to the lower curve, solve for x. I can set the upper curve equal to the lower curve, then solve for x. So if I set the upper curve equal to the lower curve, I have 1 plus radical 1 minus x equal to 1 minus radical 1 minus x. I can first of all subtract 1 from both sides. I get radical 1 minus x equal to negative radical 1 minus x. Then move this one over. I get twice radical 1 minus x equal to 0. Divide both sides by 2. Radical 1 minus x equal to 0. If I square both sides, 1 minus x equal to 0. Then x equal to 1. So x is from 0 to 1. S is from 0 to 1. F of sy is s squared times y the matching order, we must do dy first, then dx, dy, dx. So that's how we integrate from bottom to top. Which is much harder. Normally we integrate from left to right, which is much easier. Now, let me solve this integral here. What do we get? We solve the inner integral first. Take antiderivative with respect to x. Take antiderivative with respect to x. I have y from 0 to 2. If I take antiderivative with respect to x, I have s cubed over 3 times y. Evaluate from s equal to 0 to s equal to 2y minus y squared dy. Then we plug in the upper and lower limit and take difference. Then we plug in the upper and lower limits and take difference. If I plug in upper limit for x, I have, let me write y over 3 together. I have 2y minus y squared cubed. If I plug in 0 for x, I get 0. Then here we can multiply this perfect cube out. We can multiply this perfect cube out. We get y over 3 times a y cubed minus 12y to the power 4 plus 6y to the power of 5 minus y to the power of 6 dy. Then distribute y. Pull out 1/3, distribute y. Pull out 1/3, distribute y. We get ay to the power 4 minus 12y to the power 5 minus 6y to the power 6 plus 6y to the power 6 minus y to the power of 7 dy. Then take antiderivative. I get ay to the power 5 over 5 minus 2y to the power of 6 plus 6y to the power 7 over 7 minus 1/8 y to the power of 8. Evaluate from 0 to 2. Then I plug in 2 and 0 for y, and then take difference. When I plug in 2, I use my calculator. I get 32 over 105. When I plug in 0, I get 0. So the final answer is 32 over 105. For the other integral, we integrate from bottom to top. If we solve it correctly, here I'll leave it for you to verify. If you solve it correctly, you should get exactly the same answer. Now let's go back to today's class. Today we'll study multivariable probability density function. First of all, let me introduce what it is. Let S1, S2, Sn be continuous random variables. If there exists a non-negative integrable function, if there exists a non-negative integrable function, f of S1, S2, Sn, such that probability of S1 between A1, B1 and S2 between A2, B2, Sn between An and Bn, that equal to the integral from A1 to B1, A2 to B2, An to Bn, f of S1, S2, Sn, dxn, dxn minus 1, the second last one, dx2, ds1. If probability that S1 equal to A1, B1, S2 between A2, B2, Sn between An, Bn, is this integral. A1 from x1 from A1 to B1, S2 from A2 to B2, and Sn from An to Bn, f of S1, S2 up to Sn. If this probability equal to this integral, then f is called the multivariable probability density function of x1, S2, Sn. Then f is called the multivariable probability density function. Then f is called a multivariable probability density function of S1, S2, Sn. That's how we define multivariable probability density function. Note, if there are only two variables, if there are only two discontinuous non-variables, if there are only two continuous non-variables, x and y, then f is called the joint probability density function. Where such that then f is called a joint probability density function such that probability that x between A and B, y is between C and D, equal to the double integral x from A to B, y from C to D, f of sy dy dx. Here y is from C to D, x is from A to B, y is from C to D, x is from A to B. Also, since f is a joint probability function, it has two properties. Since f is a joint probability density function, it has two properties. A probability density function must always be greater than 0, must be non-negative. It may be more than 1, but it must be positive. It may be more than 1, but it must be greater than 0 for all x and y. And also, the total probability must be 1. The total probability must be 1, which means the double integral from negative infinity to infinity f of sy dy dx or dx dy, it must be 1. The total probability must be 1. So if we take double integral from negative infinity to infinity, negative infinity to infinity, f of sy, it must be 1. Next, let's look at an example. Let x and y be continuous random variables with joint probability density function f of sy equal to cx squared y if s is between 0 and 3, y is between 0 and 4. 0 otherwise. Part A, find the value of c. Part B, find each of the following probabilities. Let's do part A first. Find the value of c. We know that the total probability must be 1. So if I take integral for x from negative infinity to infinity and y from negative infinity to infinity, the total probability must be 1. First of all, let's find the support of s and y first. What's the support of x and y? Support of s and y is the set, is the closure of the set. The set of s and y in R2 such that f of sy is greater than 0. Closure, the word closure means we include the endpoint. The word closure means we include the boundary, so we include 0. For s, we include 0 and 3. For y, we include 0 and 4. Closure means we include the boundaries. Closure of a set means we include the boundary of the set. So here, support of s and y is the set x and y in R2 such that s is between 0 and 3 and y is between 0 and 4. For support of x and y, we must include the boundaries. It's the closure of the set. We must include the boundary. S from 0 to 3, including 0 and 3. Y is from 0 to 4, including 0 and 4. That's the support of s and y. Then we take integral over the support. Let's draw the support first. Support of s and y is x from 0 to 3. Y is from 0 to 4. That's the support of s and y. That's the support of s and y. Then take integral over this region. We can take integral from bottom to top or left to right. For the rectangular region, it doesn't matter. Either way, it's the same. We can take integral from bottom to top. Lower curve is y equal to 0. Upper curve is y equal to 4. So in the integral is y from 0 to 4. Then x is from 0 to 3. The function is cx squared y. dy dx, we must match the integral here, dy dx. Then for this double integral, take an inner integral first. For the inner integral, take an antiderivative with respect to y. So I treat cx squared as constant. Constant stays the same. Take antiderivative with respect to y. I get y squared over 2. Evaluate y from 0 to 4. If I plug in 4 for y, 4 squared is 16. 16 over 2 is 8. 8 times cs squared is a cs squared. If I plug in 0, I get 0. Then take antiderivative with respect to x. I get ac times s cubed over 3. Evaluate x from 0 to 3. If I plug in 3 cubed is 27. 27 over 3 is 9. 9 times AC is 72C. If I plug in 0, I get 0. So the answer is 72C. Then we know that the total probability must be 1. We set 72C equal to 1. Then solve for C. C equal to 1 over 72. That's part A. Part B. Find each of the following probabilities. First one, probability that S between 1 and 2, Y between 1 and 3. First one, probability that S between 1 and 2, Y is between 1 and 3. Let's draw the support first. Support of S and Y is a region that S from 0 to 3, Y from 0 to 4. That's support of X. We are looking for probability that S between 1 and 2, Y between 1 and 3. So we're looking for probability over this region. For this region, the lower curve is y equal to 1. Upper curve is y equal to 3. So take integral y from 1 to 3. X is from 1 to 2. The probability density function is cx squared y. The joint probability density function is cx squared y. We know c is 1 over 72, we can plug in later. C is 1 over 72, we can plug in later. Then take integral for dy, then dx. Here we do the inner integral first. Leave the outer integral the same. Take inner integral first. Take antiderivative with respect to y. That means I treat cx squared as constant. Constant stays the same. Take antiderivative with respect to y. I get y squared over 2. Evaluate y from 1 to 3. dy dx. We take dy already times dx. Then plug in the upper and lower limit and take difference. If I plug in upper limit for y, 3 squared is 9. I get 9 over 2. If I plug in 1 for y, 1 squared is 1. I get 1 over 2. So I get cs squared times 9 over 2 minus 1 over 2 times dx. 9 over 2 minus 1 over 2 is 8 over 2, which is 4. So I get 4cx squared dx. Next, I take antiderivative with respect to x. I get 4c times s cubed over 3. Evaluate from 1 to 2. If I plug in 2, I get 8 over 3. If I plug in 1, I get 1 over 3. Together, I get 7 over 3. And c is 1 over 72. So I get 4 times 1 over 72 times 7 over 3. Together, I have 28. If I simplify, I take 72 divided by 4, I get 18. 18 times 3 is 54. And I have 7 on the top. The answer is 7 over 54. That's the probability that S between 1 and 2, Y between 1 and 3. Next, find the probability that s is greater than 2. Let's draw the support first. Support is the region x from 0 to 3, y from 0 to 4. It's a rectangular region. For support of s and y, we must always include the endpoints, which means we must include the boundaries. We're looking for probability that s is greater than 2. 2 is here. If 2 is not included, we draw dashed line. We're looking for probability that s is greater than 2. In this region, s is greater than 2. So try to take integral over this region. For this region, the lower bound is y equal to 0. That's the lower curve. Upper curve is y equal to 4. So take integral y from 0 to 4, from the lower curve to the upper curve. And then x is from 2 to 3. The joint probability density function is cx squared y dy dx. Then we solve the inner integral first. Take antiderivative with respect to y. We treat cs squared as constant. Treat cs squared as constant, so cs squared stays the same. Take antiderivative for x, for y. I get y squared over 2. Evaluate y from 0 to 4 times dx. Then I plug in 4, plug in 0, and take the difference. If I plug in 4 for y, 4 squared is 16. 16 over 2 is a. A times cs squared is a cx squared. If I plug in 0 for y, I get 0. Next, take antiderivative with respect to x. I treat ac as constant. I get ac times s cubed over 3. Evaluate x from 2 to 3. If I plug in 3 for x, 3 cubed is 27. 27 over 3 is 9. 9 times 8 is 72. 72. I get 72c. If I plug in 2, 2 cubed is a. A over 3 is a over 3. Times a is 64 over 3c. Then I combine like terms. I get 152 over 3c. Then I plug in c. C is 1 over 72. If I divide top and bottom by a, 152 divided by a is 19. 72 divided by a is 9. 9 times 3 is 27. So the answer is 19 over 27. That's part 2. Now, part 3. Find probability that y is greater than 1. Find the probability that y is greater than 1. Part 3 here. Find the probability that y is greater than 1. Let's draw the support first. Draw the support first. Support is in the rectangular region. The x is between 0 and 3. Y is between 0 and 4. For the support of s and y, we must always include the boundaries. Here we are looking for probability that y is greater than 1. 1 is here. Y is greater than 1. If y is not included, we use dashed line. Dashed line represents number 1 is not included. Y greater than 1 represents all region above 1. Y is greater than 1 represents all region that's above 1. Then we take integral over this region. The lower curve is y equal to 1. Upper curve is y equal to 4. So I can integrate from bottom to top. Lower curve is y equal to 1. Upper curve is y equal to 4. Over this region, x is from 0 to 3. And the joint PDF is cs squared y. The joint PDF is cs squared y. dy dx. Let's solve the inner integral first. When we solve the inner integral, we treat x as constant. We are doing dy, we treat x as constant. So treat cs squared as constant. Take antiderivative with respect to y. I get y squared over 2. Evaluate y from 1 to 4. dx. Then plug in 4, plug in 1, and take difference. If I plug in 4 for y, 4 squared is 16. 16 over 2 is a. A times cs squared is a cs squared. If I plug in 1, I get half, which is half cs squared dx. If I combine like terms, a minus half is 15 over 2 cs squared dx. Then we take antiderivative with respect to x. That's 15 over 2 times s cubed cs cubed over 3. Evaluate from 0 to 3. If I plug in 3, 3 cubed is 27. 27 over 3 is 9. If I plug in 0, I get 0. Then 9 times 15 is 135. C is 1 over 72. C is 1 over 72. Then multiply. I can divide top and bottom by 9, which is 15 over 2 times 1 over a. That's 15 over 16. Next, that's a conditional probability. Find the probability that x is greater or equal to 1, given that y is less or equal to 2. This is a conditional probability. Find the probability that x is greater or equal to 1 and y is less or equal to 2. S is greater or equal to 1, y is less or equal to 2. Let's set out a problem first. This can be written as probability that x is greater or equal to 1 and y is less or equal to 2 over probability that y is less or equal to 2. So let's draw the support first. Support is the rectangular region x from 0 to 3, y from 0 to 4. In the numerator, we're looking for probability that x is greater or equal to 1, y is less or equal to 2. S is greater or equal to 1, y is less or equal to 2. That's the numerator. We're looking for probability that x is greater or equal to 1, y is less or equal to 2. So numerator, for the numerator, we take integral over this region here. The lower bound is y equal to 0. Upper bound is y equal to 1. Y equal to 2. Lower bound is y equal to 0. Upper bound is y equal to 2. X is from 1 to 3. The joint PDF is cx squared y. dy dx. That's the numerator. For the denominator, we only consider y is less or equal to 2. For the denominator, we only consider y is less or equal to 2. Let's draw the support again. For the denominator, we're only looking for y is less or equal to 2. 2 is here. Y is less or equal to 2. It's this region here. So for the denominator, for this region here, lower bound is y equal to 0. Upper bound is y equal to 2. X is from 0 to 3. The joint PDF is cs squared y dy dx. Then we find each probabilities, take each integral, then divide the answer. That's the final answer. Find each integral, then divide each other. That's the final answer. I'll leave the answer. I'll leave the rest for you. Next one. Find the probability that y is less than 2, given that s is less than 2. This is a conditional probability. Find the probability that y is less than 2, given that s is less than 2. Find the probability that y is less than 2, given that s is less than 2. This is a conditional probability. Let's set down the conditional probability first. Let's probability that x is less than 2 and y is less than 2 over the probability that s is less than 2. So let's first of all draw the support. Let's draw the support first. Support is the rectangular region. The x is from 0 to 3, y is from 0 to 4. For the numerator, we're looking for probability that x is less than 2 and y is less than 2. 2 is here and 2 is here. We're looking for probability that s is less than 2 and y is less than 2. Since 2 is not included, we use dashed line. Dashed line represents 2 is not included. S is less than 2, y is less than 2. That's the region. So for the numerator, we are taking integral over this region here. For this region, lower curve is y equal to 0. Upper curve is y equal to 2. So take integral for y from 0 to 2. And then x is from 0 to 2. S is from 0 to 2. The joint PDF is cx squared y dy dx. That's the numerator. For the denominator, let's draw the support again. Support is the rectangular region. The x is from 0 to 3. Y is from 0 to 4. For the denominator, we're looking for probability that x is less than 2. 2 is here. We're looking for probability that s is less than 2. In this region here, s is less than 2. For this region, the lower bound is y equal to 0. Upper bound is y equal to 4. Lower curve is y equal to 0. Upper curve is y equal to 4. X is from 0 to 2. The joint PDF is cs squared times y dy dx. Then we find each integral individually and then divide their answers. Find each integral individually and then divide their answers. That's the final answer. I leave the rest for you. Next example. When two numbers between 0 and 10 are randomly chosen, the x and y represent the value of the first and the second total numbers respectively. Part A. Find the joint PDF of s and y. Part B. What is the probability that the first number is larger than the second number? Part C. What's the probability that the second number is more than twice the first number? Part D. What's the probability that the sum of the numbers is more than 12? Part E. What's the probability that the difference of the numbers is less than 2? Part F. If it's known that the first number is more than 5, what's the probability that the second number is more than the first number? So let's do part A first. Find a joint PDF of s and y. First step, let's find a support. Keep in mind, support of S and Y is the closure of the set S and Y in R2 such that f of sy is greater than 0. For the closure means we include the boundaries. So here, since every number between 0 and 10 is randomly chosen, that means the probability is the same for every number. Probability is the same everywhere. So it's a constant function. It's a constant. Probability is the same for every x between 0 and 10 and for every y between 0 and 10. Probability is the same for every x between 0 and 10 and for every y between 0 and 10 and 0 otherwise. Since a number is chosen randomly, these two numbers are chosen randomly, probability is the same for every numbers in the interval. So the joint PDF is a constant function for s between 0 and 10 and y between 0 and 10. And here, support of s and y. Here, the support of s and y is the set of s and y in R2 such that s is between 0 and 10. For the support, we must include the endpoint. S is between 0 and 10 and y is between 0 and 10. That's the support. Let's first of all find C. Let's find C first. Once I find C, I find the joint probability density function. Once I find C, I know the joint PDF. So let's find C. Draw the support first. X is the interval from 0 to 10. Y is also an interval from 0 to 10. So the support is in this region. It's this rectangular region. The x is between 0 and 10, and y is between 0 and 10. That's the support of s and y. The total probability must be 1. So if I take integral over this region, I must get 1. The total probability is 1. So if I take integral over this region, I must get 1. So if I take integral for s from 0 to 10, y from 0 to 10, consider lower curve is y equal to 0. Upper curve is y equal to 10. Y from 0 to 10. And then x is also from 0 to 10. The joint PDF is C if x is between 0 and 10 and y is between 0 and 10. dy dx. Then take antiderivative with respect to y. Take antiderivative with respect to y. I leave x the same. I get cy. Y is from 0 and 10 dx. Then take antiderivative with respect, then plug in 10 and 0 and take difference. If I plug in 10 for y, I get 10c. If I plug in 0 for y, I get 0. Next, take antiderivative with respect to x. I get 10cx. Then evaluate x from 0 to 10. If I plug in 10, I get 100c. If I plug in 0, I get 0. Then I set 100c equal to 1. Then c equal to 1 over 100. So for the joint PDF, f of sy equal to 1 over 100 if s is between 0 and 10 and y is between 0 and 10. 0 otherwise. That's a joint PDF. That's part A. Find the joint PDF. Part B. What's the probability that the first number is larger than the second number? What's the probability that the first number is larger than the second number? Here, x represents the first number, y represents the second number. So in part B, we're looking for probability that x is greater than y. Part B, we're looking for probability that x is greater than y. Let's draw the support first. Support is a rectangular region. The x is from 0 to 10. Y is from 0 to 10. How do we find the probability that x is greater than y? Which region here? Which part here? In which part here x is greater than y? Let's first of all find the equation x equal to y first. The equation x equal to y is this line. Equation x equal to y is this line. And this equal sign is not included. X is not greater than or equal to y. Equal sign is not included. We draw dashed line. Since we don't have equal sign below inequality, draw dashed line. This dashed line represents the x equal to y. This dashed line here represents x equal to y. Usually we put y on the right side. Usually put y on the left side. Usually make it easier, put y on the left side. X equal to y is the same as y equal to x. So y equal to x represents this line. X is greater than y. It's equivalent to say that y is less than x. Probability that x is greater than y is the same as that probability that y is less than x. If y is less than x, we shade all regions below the curve. If y is less than a function of x, we shade all regions below the curve. If y is less than f of x, we shade all the region below the curve, y equal to f of x. If y is greater than f of x, we shade all regions above the curve, y equal to f of x. So if y is less than f of x, shade all the region below the curve. If y is greater than f of x, shade all region above the curve. Here, y is less than a function of x, we shade all region below the curve. So, take integral over this region. This region represents that y is less than x. Take integral over this region. For this region, we can see that the lower curve is y equal to 0, x-axis, y equal to 0. Upper curve is this line, y equal to x. In this region, that's a lower curve, that's an upper curve. So y is from 0 to y equal to x. Y from 0 to x. X is from 0 to 10. For this region, x is from 0 to 10. In the joint PDF is 1 over 100. dy dx. Solve for the inner integral first. Take antiderivative with respect to y. I get 1 over 100 times y. Evaluate y from 0 to x dx. If I plug in x for y, I get 1 over 100x. If I plug in 0 for y, I get 0 dx. Then take antiderivative with respect to x. I get 1 over 100 times s squared over 2. Evaluate x from 0 to 10. If I plug in 10 for x, 10 squared is 100. 100 and 100 get cancelled, I get 1 over 2. If I plug in 0, I get 0. So the answer is half. So the probability that the first number is greater than the second number is half. That's part B. Part C. What's the probability that the second number is more than twice the first number? Part C. What's the probability that the second number is more than twice the first number. X represents the first number here, Y represents the second number. We're looking for probability that the second number is more than twice the first number. Here we're looking for probability that the second number is more than twice the first number. So let's draw the support first. Support is a rectangular region. The x is from 0 to 10, and y is also from 0 to 10. We are looking for the probability that y is greater than 2x. In this region, which part represents y is greater than 2x? Let's draw an equation, y equal to 2x first. Let's draw an equation, y equal to 2x first. This is a straight line. Y-intercept is 0, slope is 2. This is a straight line. Y-intercept is 0, slope is 2. And what's the intersection here? To find the intersection here, when y is 10, s must be 5. So s is 5 here. At this point, x is 5. We are looking for the probability that y is greater than 2x. Since we are looking for probability that y is greater than a function of x, we show in the region above the curve. Since we are looking for probability that y is greater than a function of x, we show in the region above the curve. And here, since we don't have equal sign below inequality, it must be a dashed line here. It must be a dashed line, but when we take an integral, it doesn't matter. We show in the region above the curve. Next, we try to take integral over this region. For this region, the lower curve is y equal to 2x. Upper curve is y equal to 10. That's the upper curve. That's the lower curve. Over this region, you can see that this is the lower curve. This is the upper curve. So take integral for y from 2x to 10. X, for this region, x is from 0 to 5. It doesn't go to 10. X is from 0 to 5. In this region, x is from 0 to 5. It doesn't go to 10 here. S is from 0 to 5. The joint PDF is 1 over 100 dy dx. Then take antiderivative with respect to y. I leave an outer integral the same. I get 1 over 100 y. Y is from 2x to 10 dx. Then plug in upper limit and lower limit for y, and then take difference. If I plug in upper limit, I get 10 here. 1 over 100 times 10 is 1 over 10. If I plug in lower limit, I get 2x here. 1 over 100 times 2x is 1 over 50x. Then take antiderivative with respect to x. I get 1 over 10x minus 1 over 50 times s squared over 2. Evaluate x from 0 to 5. If I plug in 5, I get 5 over 10, which is half. If I plug in 5 here, 5 squared is 25. 25, if I take 50 divided by 25, I get 2 here. If I divide top and bottom by 25, I get 1 over 4. Then for the final answer, half minus 1 over 4 is 1 over 4. If I plug in 0 for s, I get 0, so I can ignore 0 here. If I plug in 0 for s, I get 0. So I can ignore 0, only plug in 5. If I plug in 5, I get half minus a quarter, which is a quarter. That's the probability that the second number is more than twice the first number. That's the probability that the second number is more than twice the first number. Part D. What's the probability that the sum of the numbers is more than 12? What's the probability that the sum of the numbers is more than 12? Part D. We're looking for the probability that the sum of the numbers x plus y is more than 12. We're looking for the probability that x plus y is more than 12. Let's draw the support first. The support is in the rectangular region. The x is from 0 to 10 and y is from 0 to 10. In the support, which region represents x plus y is greater than 12? In the support, which region represents x plus y is more than 12? It's hard to find it directly. So, in general, try to get y by itself. If I get y by itself, I get y is greater than 12 minus x. X plus y is greater than 12. It's the same as saying y is greater than 12 minus x. Then let's try to graph the line. Let y equal to 12 minus x. That's a straight line. Y-intercept is 12. Slope is negative 1. That's a straight line. Y-intercept is 12 and slope is negative 1. That's a straight line. Y-intercept is 12. Slope is negative 1. Since there's no equal sign below inequality, we draw a dashed line. So this is a line that y equal to 12 minus x. And since y is greater than the function of x, we choose the region above the line. Since y is greater than the function of x, we choose the region above the line. Since y is greater than the function of x. Since y is greater than the function of x, choose the region above the line. This is a line y equal to 12 minus x. This line is y equal to 12 minus x. Now, what's the intersection here? When y is 10, x is 2 here. When y is 10, x is 2. And when s is 10, y is 2 here. When s is 10, y is 2. Usually we need to find an intersection here. Next, take integral over this region. From the shaded region, we can see the lower curve. The lower curve is y equal to 12 minus x. The upper curve is y equal to 10. The lower curve is y equal to 12 minus x. Upper curve is y equal to 10. So take integral from y equal to 12 minus x to y equal to 10. For the shaded region, x is from 2 to 10. From the shaded region, s is from 2 to 10. And the joint PDF is 1 over 100. dy dx. Take the inner integral first. Leave an outer integral the same. Take antiderivative with respect to y. Evaluate y from 12 minus x to y equal to 10 dx. Then plug in the upper and lower limit for y and take the difference. If I plug in 10 for y, I get 1 over 100 times 10. If I plug in 12 minus x for y, I get 12 minus x. Dx. Then simplify. 10 minus 12 is negative 2. And double negative is positive. We get positive x, negative 2, which is x minus 2 dx. Then take antiderivative with respect to x. 1 over 100 stays the same. I have x squared over 2 minus 2x. Evaluate x from 2 to 10. If I plug in 10 for x, 10 squared is 100. 100 over 2 is 50. If I plug in 10 here, 2 times 10 is 20. If I plug in 2 for x, 2 squared is 4. 4 over 2 is 2. If I plug in 2 here, 2 times 2 is 4. Together that's 1 over 100 times 30. 2 minus 4 is negative 2. Double negative is positive. So I get 1 over 100 times 32, which is 32 over 100. If I divide top and bottom by 4, I get 8 over 25. That's the probability that the sum of the numbers, the sum of the two numbers, is greater than 12. Next, part E. What's the probability that the difference of the numbers is less than 2? What's the probability that the difference of the number is less than 2? For the difference of the numbers, we're looking for the probability that the absolute value of x minus y, or y minus x, is less than 2. The difference of numbers is less than 2. The difference, we don't know which one is larger, so we take absolute value. The difference of numbers is less than 2. Let's draw the support first. Support is in the rectangular region. X is from 0 to 10. Y is also from 0 to 10. That's the support. Now, how do we find a region like absolute value of x, absolute value of y minus x is less than 2? How do we find a region like absolute value of y minus x is less than 2? Absolute value like y minus x is less than 2. That means the difference y minus x is between negative 2 and 2. This is an inequality. If I add x to all three parts, that means y is between x minus 2 and s plus 2. That means y is between x minus 2 and x minus 2 and s plus 2. Y is between s minus 2 and s plus 2. Let's first of all graph the line y equal to s minus 2 and the line y equal to s plus 2. Let's first of all graph the left bound and the right bound first. How do we graph the equation y equal to s minus 2? That's a straight line. Y-intercept is negative 2. Slope is 1. Y-intercept is negative 2. Slope is 1. This line here, since there's no equal sign below inequality, we must draw a dashed line. Since there's no equal sign below inequality, we must draw a dashed line. But when we take integral, it doesn't matter if it's a dashed line or solid line. Dashed line means the boundary is not included. Solid line means the boundary is included. So this line represents y equal to x minus 2. Now let's graph y equal to s plus 2. That's a straight line. Slope is 1. Y-intercept is 2. So this line represents y equal to x plus 2. There are two straight lines. There are two straight lines. We are looking for probability over this region. We are looking for probability over this region in the support. We're looking for probability over this region here. How do we take integral over this region? For this region, we can tell the left side curve and right side curve. We can tell the upper curve and lower curve, because in this region, that's an upper curve, this is a lower curve. In this region here, that's an upper curve, that's a lower curve. And same thing for left side and right side curve. In this region here, that's a left side curve, that's a right side curve. But in this region here, that's a left side curve, that's a right side curve. Since we can clearly tell left side and right side curve, or upper and lower curve, we must cut this region into several pieces. So let me first of all cut this piece into one piece, two pieces, and three pieces. Let's call this region R1, R2, and R3. Let's take integral over region R1, R2, R3. And by the way, what's the intersection here? What's the intersection here? On this line, y equal to s minus 2, when y is 0, s is 2 here. On this line, y equal to s plus 2 equal to 2, y equal to s plus 2. This line, y equal to s plus 2. When y is 10, s must be a. So from region 1, for region 1, s is between 0 and 2. For region 2, s is between 2 to a. S is from 2 to a. In region 3, s is from a to 10. So we must take integral over all three regions. So take integral over all three regions. We must take integral over all three regions. Integral over region 1, region 2, and region 3. dA. dA represents two-dimensional integral. dA represents two-dimensional integral. A represents area. Taking integral over this area. Now, let's take the first integral first. First integral. In region 1, lower curve is this line, y equal to 0. Upper curve is this line, y equal to s plus 2. X is from 0 to 2. And the PDF, the joint PDF is 1 over 100. The joint PDF is 1 over 100. dy, dx. Solve the integral first. Take antiderivative with respect to y. I get 1 over 100. Antiderivative of dy is y. Y varies from 0 to s plus 2. Then plug in the upper and lower limit and take difference. If I plug in upper limit, I get 1 over 100 times s plus 2. If I plug in the lower limit, I get 0. Then take antiderivative with respect to x. I get s squared over 2 plus 2x. Evaluate from 0 to 2. If I plug in 2, 2 squared is 4. 4 over 2 is 2. If I plug in 2 here, 2 times 2 is 4. If I plug in 0 for x, I get 0. So the final answer is 6 over 100. The final answer is 6 over 100. That's the integral over region R1. Next, take integral over region R2. Take integral over region R2. For region R2, we can see that this is a lower curve. This is an upper curve. Lower curve is y equal to s plus x minus 2. Upper curve is y equal to s plus 2. In region R2 here, x is from 2 to a. X varies from 2 to a. The joint PDF is 1 over 100. The joint PDF is 1 over 100. dy dx. Do dy first. dy dx. Then solve the inner integral. Take antiderivative with respect to y first. I get 1 over 100 times y. Y varies from s minus 2 to s plus 2 dx. Then plug in the upper and lower limit, take difference. If I plug in the upper limit, I get x plus 2. If I plug in the lower limit, I get x minus 2. Simplify. X and x get cancelled. 2 plus 2 is 4. 100 times 4 is 4 over 100 dx. Next, take antiderivative with respect to x. I get 4 over 100 times x. X varies from 2 to a. If I plug in a, I get a. If I plug in 2, I get 2. A minus 2 is 6. 6 times 4 is 24. I get 24 over 100. That's the integral over region 2, region R2. That's integral over region R2. Next, take integral over region R3. In R3, the lower curve is this line, y equal to s minus 2. That's the lower curve. Upper curve is this line. Upper curve is y equal to 10. Upper curve is this line. That's y equal to 10. Lower curve is y equal to s minus 2. Upper curve is y equal to 10. And in R3, x varies from a to 10. In R3, x varies from a to 10. The joint PDF is 1 over 100. Then take dy times dx. Solve the inner integral first. Take antiderivative with respect to y. I get 1 over 100 times y. Y varies from x minus 2 to 10 dx. Then keep x the same. Plug in the upper and lower limit for y and take difference. If I plug in 10 for y, I get 10. If I plug in s minus 2 for y, I get s minus 2. Then simplify. I get 10 plus 2, which is 12, minus x dx. Then take antiderivative with respect to x. I get 1 over 100 times 12x minus s squared over 2. Evaluate from a to 10. If I plug in 10 for x, I get 120. 10 squared is 100. 100 over 2 is 50. If I plug in a for x, 12 times a is 96. A squared is 64. 64 over 2 is 32. That's 100 times 70 minus 64, which is 6. I get 6 over 100. So for the final answer, we add all three integrals together. For the final answer, add all three integrals together. So the probability that y, absolute value of y minus x, is less than 2, equal to the sum of all three integrals, 6 over 100, 24 over 100, plus another 6 over 100. The sum of all three integrals. 6 plus 24 is 30. 30 plus 6 is 36. We get 36 over 100. If I divide top and bottom by 4, I get 9 over 25. That's the probability that the sum, the difference of two numbers is less than 2. That's the probability that the difference of two numbers is less than 2. Next, F. If it's known that the first number is more than 5, what's the probability that the second number is more than the first number? Here, x represents the first number, y represents the second number. If it's known that the first number is more than 5, what's the probability that the second number is more than the first number? This is a conditional probability. If it's known that the first number is more than 5, what's the probability that the second number is more than the first number? If it's known that the first number is more than 5, what's the probability that the second number is more than the first number? This is a conditional probability. So let's first of all set out the problem. For the numerator, we want s to be greater than 5 and y to be greater than x. For the numerator, we want a probability that x is greater than 5. We must find probability for each numerator and denominator individually, and then divide the answers. We must find a numerator and denominator individually, and then divide the answers. Let's find the probability for the numerator first. So first of all, let's draw the support. Support is the rectangular region where x is from 0 to 10 and y is also from 0 to 10. That's a support. For the numerator, probability that s is greater than 5, y is greater than x. 5 is here on the x-axis. This region here is s is greater than 5. This side here, the region on the right side here represents s is greater than 5. And also we want y to be greater than x. Let's draw the equation y equal to x first. Y equal to x is this line. This is the line y equal to x. Since y is greater than the function of x, we choose the region above the curve. So for the numerator, we're taking integral over this region. In this region, the lower curve is y equal to x. Upper curve is y equal to 10. So for probability that s is greater than 5 and y is greater than x, we're taking integral y is from x to 10. That's the lower curve, that's the upper curve. And in this region, s is from 5 to 10. In this region, s is from 5 to 10. And the join the PDF is 1 over 100 dy dx. That's a joint PDF. Here we solve the inner integral first. So leave an outer integral the same. Solve the inner integral first. I get 1 over 100 times y. Y varies from x to 10 dx. Then we plug in the upper and lower limit and take difference. If I plug in upper limit, I get 10. If I plug in lower limit, I get x. So I get 10 minus x dx. Then take antiderivative with respect to x. I get 10x minus s squared over 2. Evaluate from 5 to 10. If I plug in 10, 10 times 10 is 100. If I plug in 10 here, 10 squared is 100, 100 over 2 is 50. If I plug in 5, 10 times 5 is 50. 5 squared over 2 is 25 over 2. That's 1 over 100. 50 minus 75 over 2. 50 minus 75 over 2 is 25 over 2. If I divide top and bottom by 25, I get 1 over a. That's a numerator. That's a numerator. Next, let's compute the denominator. So let's draw another graph. Draw the support first. Support is a rectangular region. The x is from 0 to 10. And y is from 0 to 10. We're looking for probability that s is greater than 5. 5 is here. That's a region that s is greater than 5. That's a region that s is greater than 5. So, for probability that s is greater than 5, lower curve is y equal to 0, upper curve is y equal to 10. X is from 5 to 10. X values in this region, x values from 5 to 10. And the joint PDF is 1 over 100 dy dx. Solve for inner integral first. Leave an outer integral the same. Solve for inner integral first. I get 1 over 100 times y. Y varies from 0 to 10 dx. If I plug in 10 for y, 1 over 100 times 10 is 1 over 10. If I plug in 0 for y, I get 0. Next, take antiderivative with respect to x. I get 1 over 10 times x. X varies from 5 to 10. If I plug in 10, I get 1. If I plug in 5, I get 5 over 10, which is half. 1 minus half is half. So for my final answer, probability that y is greater than x, given that s is greater than 5. The numerator is 1 over a. The denominator is probability that s greater than 5, which is half. 1 over a over half is 1 over 4. That's the probability that the second number is greater than the first number, given that the first number is greater than 5. That's the answer.